The two red ones are what? Gas. What's the blue one? Liquid. What's the black ones? Solids. Good. So we got that. We wrote down iodine sublimes, right? Which means, what did we write? Why does it sublime? It goes solid to a gas, right? But why does it do that? Weak forces. The particles are like this. Look up here. Particles are close together, and then in between the particles, there's like imaginary force, but it's real. It's kind of like gravity. You can't touch gravity, but you know it's there because you jump up and fall back down. Okay, the moon doesn't float away. We don't float away into space. We're going around the sun. The moon's going around us because of gravity, right? So gravity is my analogy because everyone sort of understands that. At least you know it exists. Gravity, when I say forces of attraction in chemistry, I want you to think kind of like gravity. So particles kind of hover near each other, not touching. So solid particles are really, really close in iodine, and there's a little bit of space, and that space has a weak force of attraction. And that weak force, kind of like magnets or gravity, is easily broken. That's why the particles spread out and become a gas so easy. So we did talk about that. I just wanted to repeat that. And they only exist in compounds because they are so reactive. Did we also write that? Yes or no?
I think so, yeah.
Okay. Good, that was it. We hit everything then. We're done with the halogens. All right. So, next thing I want to do is talk about some random elements here. Oh, how many valence electrons do the halogens have? 7. How do you know that? Because we wrote it down. Also, remember the trick. How many valence electrons here? 1. How many here? 2. Skip the fools. How many here? 3, 4, 5, 6, 7, 8, except for helium.
Are they dirtbags because they don't have to out all that?
I don't like that word.
I call them that because they have a lot of electrons in what's called the d orbitals. So they're called the d block. D block dirtbags. That's why. Yep. Okay. Carbon. Let's talk about carbon. Why are we talking about carbon? Because carbon is found in all what? Living things. All living things. Plants, animals, insects. Think organic when you think carbon. So this idea of organic chemistry, it's a huge, not idea, topic. Organic chemistry is a huge part of chemistry. People spend their entire lives just researching like one little thing in organic chemistry. Everything you're wearing in this room, I would bet, this has to do with organic chemistry. All your clothes has carbon in it. This plastic water bottle has carbon in it. This has carbon in it. This Fitbit probably has carbon in it. Yeah, I would say it does. This rubbery plastic. Carbon's everywhere. Organic chemistry is responsible for almost everything that has carbon. Plastics, clothing. Think about how many things are plastic. Think about clothes, think about plastic. Take those two things off the planet. There's not much left. What's left?
Actual real stuff.
Metal. And that's about it. So I guess trying to convince you of how kind of important the study and the reactions of carbon is or are. So found in all living things, organic, think carbon. There are 3 allotropes of carbon. Underline that word, allotrope. We're going to define that. Allotrope. Same element, but different molecular structure. Same element, but different molecular structure. What the heck does that mean? Put a little arrow here. How atoms are arranged. So right now, let's say every single one of you in this room, every single student in this room is a carbon atom. Okay? And you're arranged in your specific seats. And I set that up with the seating chart. Well, if I said everybody stand up and go to a different seat, technically, you would be arranged differently. Yes, you're still in rows, but let's say Devin got up and sat next to Zach. Probably would happen. Okay? Or Shelby came up front. Kristen went in the back, or whatever. Yeah, you're in the class, you're in the rows, but you are technically in a different arrangement because you move seats. That's what this means. Okay, there's 3 different versions of carbon. Substances that contain just carbon. I'm going to show you the video here in a minute. Okay, it's going to show you the 3 different types. Does anybody know any of them? Excuse her. Anybody know any of them? One of them is really expensive.
You said question again?
Yep, one of the forms of carbon. One of them is really expensive, really strong, really hard. Diamond.
Jake said first. Yeah. Just letting you know.
Okay, so Jake's diamonds. Diamond. There's another one. You're writing with it right now, some of you. Graphite. The last one no one will ever get, so I'll give it to you.
Wait.
Hold up.
Wait.
It's called buckyball.
I knew that.
Oh, yeah.
It's called Buckminster fullerene. Buckyball. Buckyball. So what I'm going to do now is show you the difference between them, all right, using the video here. And you guys already know diamond and graphite look extremely different, okay? Look extremely different from each other. So their properties are different, right? Why? Here's why. Even though diamond is carbon and graphite is carbon, because of the structure, diamond is like clear, kind of looks like glass, right? Graphite's gray, black, slippery a little bit, okay? Buckyball looks like soot, actually. Like, you know, you have a fire or a chimney, the black stuff, that's what buckyball looks like. So all 3 look different and they have different properties because of how the atoms are arranged. Again, if I told you to get up and change seats, it would change your arrangement. Well, when that happens to carbon, properties change. So let me show you this. So I'm going to hit the lights.